Yeah, hello everyone, and thanks for joining this talk. So I want to present the LLVMLinux project, and we were at the last Plumbers, and exclusively for Fosdem, we can present the T-shirt, yeah, because the feedback was really nice, but you have no T-shirt, so here it is. So what's this project about? First of all, well, why do we want to compile the kernel with Clang? Yeah, we have GCC, we have a compiler, so why? Well, one reason is we get a few more diagnostics out of Clang. Yeah. In the first line, you see the output from GCC, in this case 4.2. And the second line, that's the same error for Clang, and you get more informative output with Clang. That's also the reason why, for example, Google, they build their huge code base side by side with GCC and Clang. They use GCC in production, but they build with Clang for the diagnostics. Yeah. So that's one example why that could be interesting. For the kernel, well, we have a lot of such warnings, errors, and so on. So that can be quite noisy, and we have to find out, okay, what's useful now and not. But still, we get a lot of information out of this, and more informative hints on what might be wrong at this place. Also, we get more informative hints on what to do, what to fix. So even you see here those nice caret pointers. So Clang knows how, in more detail, not just something went wrong and this statement. So it went wrong at this position. So that's one of the strengths of Clang. Comparison for the macros. In GCC, you just get an error. Well, we have, in this macro, we have an error or invalid operands. In Clang, we get the macro expanded, so you get to know where in the maybe daisy-chained macros the bad condition happened. Yeah, so it's not then up to you to dig through maybe multiple macros and find the spot where the bug is. You get a more detailed output here. Another thing which is interesting here is that Clang allows more things. Like we have a static analyzer, where we can create an analysis of our code flow, and we can also get detailed information on what goes wrong, for example, in this branch here. We are currently working on adding this analyzer, the checker, to our compilation to the Linux kernel. It's still in an early stage. And of course, the kernel is a huge code base, but we are working on this. And we are curious to see what we will find here, what can be improved in the kernel. So, what else? LLVM is also part of a few more projects. For example, it's an integral part of a render script in Android. It's part of the Gallium 3D engine in multiple ways. And there is, for example, also a full build of Debian with Clang Tomorrow, Sylvester will have his talk, and he will talk about this in more detail. So that's where Clang is already in use. There's also a FreeBSD port, and also Minix 3 is using it. So that's quite interesting. So now back to the Linux kernel, back to our LLVMLinux project. So, well, of course, our goal is to build the Linux kernel with Clang. For as much architectures we can reach, Clang is actually inherently a cross-compiler. Clang uses a kind of intermediate representation. So you parse your code, get it into an intermediate representation, can do all sorts of optimization on that intermediate representation, and finally you dump it into the architecture-specific code. So apparently Clang is a sort of a cross-compiler already. So targeting multiple architectures is actually quite easy. So what we want to do is we want to enable building the kernel with Clang. Currently we reach that on ARM x86. We are looking into MIPS, but that doesn't have a lot of traction right now. Now, the goal of the project is also to find anything that's kind of a blocker. So we have a few spots where kind of the kernel tends to use a really GCC specific, and Clang maybe because of its architecture cannot do that. Yes, so there are a few things where we have to find what's the blocker here, and actually where do we solve it? Yeah, be it kernel or be it Clang. We are no fork of the kernel or Clang. Yeah, we are kind of aggregating patches for both projects, and we are contributing them back to the upstream, to Clang and to the Linux kernel. Currently, for Clang and LLVM, our patch set is quite small. It's like 5 for each LLVM and Clang, so that's kind of up to 10. For the kernel, our patch queue is quite bigger because we have, especially on x86, a few spots where we have to kind of jump through a few loops to get it working. And we want to kind of get those patches in a shape where we can move them into mainline. So you can find information about the project here, llvm.linuxfoundation.org. We have their project status page. We have the roadmap there. And you can find also our links to the build board there. We have a build board running, which continuously builds against kernel, Clang, LLVM upstream, of course with our patch set on top. So we are actively tracking the development head, so we can enable the work on upstreaming the patches. Architecture supported, I will go into more details in the next slides. So website, you can reach us on IRC. So we are on the channel LLVMLinux on OFTC. You can reach me on my nick DL9PF there. So just drop by the channel if you have any questions or if you need support, if you want to try it out. We have a mailing list, LLVM Linux, so you can post and subscribe to that list. If that was too fast to note it down, take a quick shot on the QR code. I will present it on the as last slide too. All right, now show me the code. Just go to git.linuxfoundation.org/LLVMLinux.git. So what do you get? So it's no clone of the kernel. It's no clone of the LLVM and Clang. What you get there is a kind of a make framework, yeah, a set of make files. It will download the kernel, download LLVM, download Clang, apply all patches, and then build it. So in the end, you get a compiled kernel, kernel compiled with Clang out. We still we are working on support for K-build, so we want to make all those nifty changes and all those nitty-gritty workarounds. We want to make them available in the kernel's K-build system, so actually we can kind of throw away our scripts sooner or later. So that's hosted there. We also do testing in this framework. So, for example, for the ARM targets, we have a QEMU system ARM target, where you just can kind of go to the subfolder, hit make, and it will build everything and even boot a rootfs and test it. Yeah, so complete. We can do the complete cycle until it runs. So that's what we actually use. What's our tool for our work in kind of getting the patches working, getting everything working, and kind of for tracking upstream and for pushing our changes upstream. Just an example on how to use it. So you just check out the JIT. You could go to targets vexpress, and the simple case would just you hit make. Yeah, this will do everything for you, and it allows you even to boot a test system with QEMU and verify it works. There are a few targets. We have the Versatile Express, but also there's a target for the MSM boards. i586, x86-64, Raspberry Pi. I think we will merge a BeagleBoard target in the next days, if it's not merged yet. But that's pretty rough. But, well, it's quite easy to set up your own target. Yeah, it's just copy the template, make a few adaptations, and boom, you have your own target. So it's quite easy to create your own versions, create your own adaptations. x86, currently we are, the only working target here is kernel 3.3, because we have currently huge problems on mainline. That's because we had some rewrites in the real mode code, and that's still making troubles right now. But we are working on that. Okay, so what do we have to do? Flace is a big problem for us. We are debugging segment differences, so if you compile with GCC and if you compile with Clang, the output has different style of linking. So that's what we are debugging, moving x86 to mainline. That's our current efforts. So if you have any more questions, drop by on ISC, check it out, and build it. We are always happy if you just ask, hey, I have this problem, or what's going on. Ask us on IRC, we are there. All right.